Jai Hind everyone. My name is Pooja Pandey and I'm assistant professor in the MC department in the Ajay Kumar Garg Engineering College in Ghaziabad. And today I'm going to discuss a software solution to the critical section problem in the operating system. And according to the AKTU University, Lucknow, its code is BMC 203 in the MCA course. Okay. Now, today I'm going to discuss my problem, that is, or you can say my presentation is on the software solution to the critical section problem, and here I am going to discuss the Peterson algorithm and what are the comparison between the Dekkers algorithm and the Peterson algorithm. And earlier in my previous video, if you will search that, you will find out that what do you mean by the critical section. In that I have discussed that what do you mean by the critical section, and it's what is the problem we are facing, or what is the problem of the critical section problem. Then in that PPT or in that video, I have already discussed the 3 requirements must satisfy for the critical section solution, and in that video only I have discussed that the software solution to the critical section problem, and there are mainly 2 solutions. In that presentation, I have already discussed the Dekker solution, that how the pseudocode works and how we encounter the problem, or what are the limitation of the Dekker solution. Here we will discuss about the next algorithm, that is a continuation of the software solution to the critical section problem, and then after it, the last, we will discuss the we are going to discuss about the comparison between the Dekker solution and the Peterson's algorithm, and why we are working on the Peterson algorithm. Okay, we will discuss the working of this, how the Peterson algorithm works. We will discuss with an example. Then how this is going to satisfy the 3 condition, the 3 condition, that is mutual exclusion, if I am discussing mutual exclusion, progress and the bound weight. These 3 conditions should be satisfied by the Peterson algorithm. Then at the last, student will be able to compare it with the Dekker's algorithm. So now let's start our presentation. That if I take the recap of the previous lecture, you have studied that critical section problem, and according to the critical section problem, what is a critical section? It is a part of the code where the shared resources are the access, and we find out the problem when multiple resources are wanted to access at the same time. That will lead to the problem of the race condition. To overcome that problem, or to overcome the race condition problem, we will say that it must satisfy the 3 parts, that is, you will say that mutual exclusion, progress and the bounding weighting. Again, I am saying that mutual exclusion means that this is a recap, so I am just taking a recap for that what do you mean by the mutual exclusion? It means that one process at a time only one process will enter into the critical section, and that will be a mutually between the 2 processes. Okay, you can go and I will wait. After you will complete, I will go. That is a mutual exclusion, and normally we use in the operating system, we use a word mutex for it. So in the further videos, you have to keep in mind, for the mutual exclusion we are using the word mutex. Now for the second property, or for the second solution, if I am saying progress, it means that it is not kept idle. If the process, we say that the process, it is not kept idle. Whoever is available, they just go. If that part is empty, okay, that portion is empty, then whoever process P1 is available, then process P will go. Process P0 is available, then process P0 will go. It is not going to wait for the other process. So that is what your progress. In the bounded waiting, we are just giving the turn to the each. We are keeping requirement that each process should get equal turn, and there should be no starvation should be there. So these all critical section problem will be solved only when these 3 properties, or these 3 properties are satisfied. Okay, now we have seen in the Dekker's algorithm, which was the first correct software solution, we have seen that it was a first software solution, but we find out that the logic of the Dekker solution was very complex, and due to which its implement is also very tough. That's why, to simplify this complexity, Peterson proposed a simple solution, and that is what we are going to call it as a Peterson algorithm. So normally Peterson algorithm we have was normally proposed by the Gray Peterson, and on this person only this algorithm has been named Peterson algorithm. And this Peterson algorithm is a very simple and elegant software solution compared to the Dekker solution, and it was also designed for the two process, and it uses the shared variables to control the entry into the critical section. See, this line what I have written here uses shared variables to the control entry into the critical section. It is a very common line whenever you are discussing about the any problem further in the operating system. When you are discussing the semaphore, when you are discussing the monitors, you have to keep in mind that there will be a condition requirement must satisfy, that is your mutual exclusion. And mutual exclusion says that mutual exclusion, okay. And when we are discussing the part that is critical section, it means that we are using the shared variables to control the entry into the critical section. So this line will be used in every algorithm, okay. Now till now we have understood that Dekker's algorithm is a very complex. Why? Because of its complex. We are using the while loop, and we are taking the turn is equals to j, then flag is equals to I. Whatever that process are going on, it is keeping our process very tough and very complex. That is why what we are saying that our Peterson algorithm has been designed in a such a way that it is very easy to understand as compared to the Dekker's algorithm. Right now, when I am discussing about the variables used in the Peterson algorithm, it means that we are using the two variables. We are using the two variables, that is Boolean flag 2 and the int. Here we are using the two variables. If you see that, flag and the turn. Again, flag will indicate which process want to enter the critical section, and turn will indicate whose turn it is to enter in the critical section. That is what we are saying, okay. So this is what the Peterson algorithm, and these are the two most important variables we are using for the Peterson algorithm, that is flag and the turn. Flag indicate the process PI want to enter the critical section, and turn indicate whose turn it is to enter the critical section, right. Now, again, if you all have kept in mind, or if you have seen my previous video for the Dekker's algorithm, you will find a very common thing here. Again, what I am taking here, you have to see, we are taking the flag. It is in the case of the Boolean, right? That is 1 and 0, okay. Now, I am taking the variable turn is equals to false, okay. Now, I have taken that flag 0 is equals to flag I, 1 is equals to false. It means we are taking the two processes Pi and Pj. Again, I am taking. Here you have to understand, and that both processes want to access at the equal time, right? They wanted to enter into the critical section at the same time, and for that same time we are applying the Peterson algorithm to find out the software solution for the critical section problem. Now here, if you see in the process Pi, we are using that. What you have to keep in mind what I am saying. Here what you have done, again in the previous Dekker's algorithm, flag of I is equals to true. It means that the flag I, or the process I, has raised its flag that I wanted to enter in the process. Now here, again, for the process Pj or for the process J, what I am saying that here my flag of J, it means that J process has raised his hand or her hand that okay, my turn is there, right? Again, what I am checking that here turn is equals to J, okay? In Hindi we say that pehle aap. Again he is checking ki theek hai, aap pehle aa jao. So flag of I is equals to turn. Here from there it is checking that turn, if turn is equals to J, let us suppose that turn kiska hai? J ka. Then what will we check that? If flag of J is true, right, and turn is equals to J, then which process will we go? It will execute the process Pj, right? Then after it is completed, then it will enter and it will do all these process. Here also what? The same process is going on. Now the difference is there between the Peterson algorithm and the Dekkers algorithm. You have to keep in mind that let us suppose that this process is taking the time 4 and this process is taking the time 6. So when we are doing the programming, we always take that x is equals to 4, x is equals to 6. Let us suppose these two variables we have taken in the programming. At the last, which variable will be updated? X values which we are going to update, we will take that x is equals to 6 because it has come at the last turn. Okay, whoever coming the last, we will update the value from here. So it means that if process Pi has taken the 4 and process Pj has taken the 6, it means we will update process whose turn will be there? Process J turn will be there. So here in process Pi, when I is there, J will be completed because what updation is going on? X is equals to J. It means the J1 will be updated. Okay. Then only the critical section will, then only the remaining part will be go as it is what the in the Dekker solution was going on. So this will, you see that according to this, we are just updating who is coming on the last. So we are not going, this logic is very simple. We are not checking whose turn on it. We are just saying who is coming on the last and we are updating that last person to access that, or we are updating our process according to that. So it is very simple. So that is what about your Peterson algorithm. Now, if I am going to discuss the working of the Peterson algorithm, there are the 3 cases of the Peterson algorithm according to the pseudocode what we have discussed in the previous slide. It means that the first case is that it means only one process want to enter that. What does it mean? It means that suppose P0 or Pi, the flag 0 is equals to true. Okay, P0 set the flag 0 is equals to true. It means that the other flag is false. If one flag is true, it means that other flag is false. That it means that while condition will be failed and P0 will enter directly. Okay, that is a case of your mutual exclusion. Now, both second case, if you discuss that both process want to enter, again both process want to enter, right? So it means that both set their flags to the true. If you remember that flag of I is equals to true and flag of J is equals to also true, but both are setting their turn to the other process. What does it mean? That it means that flag of I is equals to true, right, and flag of J is equals to true, right? Now it means that both set their flags to true, but both set the turn to the other process. So turn will be, turn is equals to J and turn is equals to I. Okay. So it means that the process whose turn is not favored wait, the process who is not favoring the wait, only that process or only that one will enter in the critical section. It means the progress condition has been satisfied, right? Now, for the case 3, if you say that if process set flag of I is equals to false, other process can now enter and fairness is maintained. Okay, it has decided that which process has got the turn, and only that process will be is going to enter in the critical section, or is going to take the process. Okay, so these 3 conditions, this is the working of the Peterson algorithm. First one is only one process want to enter. Second case is both the process want to enter, and case 3 is after leaving the critical section, what will be happen. So according to the Peterson algorithm, there is no starvation, there is no complex logic is there, and it was very easy to implement, and it was very easy to implement on the software part. Okay, so that's why we it was seen that Peterson algorithm was very easily adopted as compared to the Dekker's algorithm. Now, how Peterson algorithm satisfy the 3 conditions? That was a 3 steps, 3 cases that was working on the pseudocode. Now, we are going to see that how Peterson algorithm satisfy the 3 conditions. The first one is your mutual exclusion. If both the process cannot enter the critical section at the time, we know. So, the condition here, flag of j and turn is equals to j, it ensures that only one process will wait. It means that only one process passes the while loop and enters the critical section. It means that it satisfies the mutual exclusion property. Now, for the progress, we know that if no process is there, we will make sure that the process who is available, we will allow that process to enter in the critical section. That is what the progress is. If no process is inside the critical section, the process that want to enter can proceed, right? Now, the decision of who enters next is not postponed indefinitely, right? It is not postponed. Who is available, we are allowing it by sequence, by number wise, right? Who is available. Who is not there, we are just leaving that. It doesn't mean that we are waiting for the process which is not available. No, we are not going to fail. Then that is satisfying the progress part. Okay. Now, the third is your bounded waiting. In bounded waiting, if you remember that we are taking the variable turn, and due to which there will be a no condition of the starvation, there will be, and we will find out that there will be, we are ensuring with the turn variable the property fairness. That is, each and every process is going to get the equal time, right? So, a process cannot be postponed forever, and each process gets a chance to enter the critical section. So, this how we see that Peterson algorithm is satisfying these 3 conditions, so we can solve the problem of the critical section. Now, it is a very important thing. Many students get confused that, okay, Dekker's algorithm is working in the same time and Peterson algorithm. No, there is a comparison chart between the Dekker's algorithm and the Peterson algorithm. When we are discussing about the complexity, in terms of the comparison about the complexity, it means that Dekkers has got the complex logic, while the Peterson has got the simple and the elegant. How? If you remember, in the pseudocode, in the complex logic, in the Dekker's algorithm, we are entering in the while loop, then we are checking the turn, then we are doing the flag. But in the Peterson, we are doing it at the same time for that specific, for the other process, and if that condition doesn't satisfy at a time, we are using the next process. So, we can see that the Dekker has got the complex logic, while the Peterson has got the simple and the elegant logic. In terms of the readability, if I say Dekker's algorithm and Peterson algorithm, we will find out that when we are studying the pseudocode of the Dekker's algorithm, it was very difficult to understand whose turn was there or whose flag we are going to raise. But in the Peterson algorithm, we have used a less code. So that's why it is very easy to understand. Okay, flag I is equals to 0, then flag I, okay, so sorry, if flag of j if permission is given to the next process and turn is also the next process, that we are finding very easily in the code when we are seeing that. Okay, this code means this, but in the Dekkers we are finding it very difficult, right? If you remember that Dekkers, there is a multiple nested condition, and due to the multiple nested condition, it is very tough to understand that logic, right? While in the Peterson, it is very cleared and the structured. Okay, number of steps are also less. But what we find out in the Dekker's algorithm and in the Peterson algorithm, that the variable, what we are using, the variable that is flag and both we are using the same. They are satisfying the condition mutual exclusion, bounding waiting. Yes, they are satisfying. Practical use, mainly both are used for the practical use. So these are the solution for the critical section. So in this presentation, I have discussed about the Peterson algorithm. We have taken a recap for the critical section, its problem, its 3 steps. Then I have discussed the Peterson algorithm, who has discovered, what are the steps we are taking, what are the cases, 3 cases we are discussing in the pseudocode, how they are satisfying the 3 conditions of the critical section solution. Now we are at the end of this presentation. So here what are the conclusion we have discovered here? It means that the software solutions were early attempt to solve the synchronization. Okay, we have find out when we have discussed the Dekker algorithm in the previous video and the Peterson algorithm in this video, we have find out that it was a very early attempt to synchronization. Peterson is just an improved version of your Dekker's idea. Now both are working on only for the 2 processes, and when we are talking about the today era or for the current era, we are not working on the software solution. So these things we are not using. What we are using, that modern system is using the hardware based solution, and that hardware based solution I am going to discuss in my next video lecture. There you will find out that how we are able to find out the solution for the critical section using the hardware method, right? So this is a conclusion of my today's lecture. So thank you all. Jai Hind.